So we're going to consider another example now using the direct stiffness method, just in one dimension and just for truss elements. And the example we're going to do, very similar to the one before. We have 3 bars, bar 1 with cross-sectional area A, Young's modulus E and a length of L over 2. Bar 2 has length L, cross-sectional area A and Young's modulus of E. And bar 3 has now cross-sectional area of 2A, length of L and Young's modulus of E. Again, let's draw what the similarities are. All 3 bars are connected in the exact same way as in example 1. The support condition at node 3 is identical. The only thing that's changed in the entire system is that we've moved the external force from node 1 to node 2, and now it's acting in the positive x direction. So as a result of these changes, or things that haven't changed indeed, the element matrices are identical. So the elements have exactly the same dimensions and properties, so they don't change. As a result of the bars all being connected in exactly the same way as previously, the global matrix or the global system of equations is again identical. And because the support condition is the same, we know that U3 must be equal to 0. The reduced matrix or the reduced stiffness matrix will again be identical. What has changed now though, and scroll down, so we have changed element matrices identical, global matrix identical, reduced matrix identical, but what has changed is our external force vector. Previously we had a force minus F applied to node 1, no force applied to 2, and an unknown force F3, the reaction force at 3. Now that this has changed, let's go back to the picture. We now have the external force F at node 2, so we insert that in the second row of our external force vector. So F, and it's in a positive direction, so it's positive F. And we have no external force at node 1, so the value there is 0, and we still have the unknown reaction force F3 at node 3. And so we can rewrite our reduced system of equations, getting rid of our bottom row and our third column from the stiffness matrix. So we have 0 and F. The force vector is equal to AE divided by L. Now 2 minus 2, 5, multiplying by the unknowns U1 and U2. And that's all that's changed in this situation. Okay, so we move on to another example. We've got exactly the same system of bars 1, 2 and 3 with exactly the same properties, and we've kept the external force F on node 2. What we have added to this example is we've decided that we're going to fix node 1. So we know that U1 must be equal to 0. And as a result of this, what has changed? What has stopped the same? So we can see that each of the elements is exactly the same. The bars still have the same properties and the same lengths. Therefore, when we add the elements together, the configuration or how the elements are connected to each other is still the same. So the global matrix is still identical. The external force vector is still exactly the same as the external force vector we had in example 2. Apart from, you might consider that we have an unknown force F1. We don't know that that's 0 in this case. And the reduced matrix now changes. So what we should do is go back to the full system of equations that we wrote down. And if we write those system of equations down, we had AE divided by L, then we have 2 minus 2, 0, minus 2, 5, minus 3, 0, minus 3, 3, multiplied out by the displacements u1, u2, u3 equal to f1, f2, f3. So in this situation now, we now know that u1 must be equal to 0 because it's supported. We know that u3 is 0 because it's supported. And we know that f2 is a known external force F. And because we have two zero displacements, we have two rows of this system of equations that we already know the answer to, so we can just cross out these rows, and because we're going to be multiplying out by zeros, we can also cross out the columns, and we're left with a very simple equation for 5AE over L multiplied by U2 equals F, and we can rearrange that to get the U2. So our reduced matrix was completely changed. So for a final example, example 4, we're going to consider the case where we've took the previous example, exactly the same bars, exactly the same external force F applied to node 2. But in this case, we've removed the supports at nodes 1 and node 2. So we can see we don't have the support here and we don't have the support here. The system is just left flying in space. Okay. So we know as engineers this is daft. We cannot get static equilibrium. We can get dynamic equilibrium. That's something else we'll look at in this course. But for now, we know we cannot get static equilibrium. Okay, so let's see how this plays out when we use this method. Okay, let's have a look. At nodes 1 and 3, we know neither the displacement or the external force. So, and both the global and the reduced system of equations need to be changed, and so we get a full system of equations with unknowns u1, u2 and u3, and we have no external forces at f1, no external forces at f3. As a result of this, let's try to see what we can calculate. From that first, the top equation there, we get, and we follow it through, that 2a over L times by u1 minus 2AE over L multiplied by U2, and rearrange that, we get U1 equals U2. Okay, I can maybe believe that. If we look at the third equation now, it doesn't involve an external force F, so it's easy to rearrange. We can see that we have minus 3AE over L multiplied by U2, plus 3AE over L multiplied by U3. Therefore, U2 must be equal to U3. So again, and that would also mean from the equation above that U1 equals U2 equals U3. Okay, no problem so far. However, when we go to the third equation, let's write out the third equation we get, and let's zoom in a little bit closer. We'll get F, the external force applied, equals minus 2AE over L multiplied by U1 plus 5AE over L multiplied by U2 minus 3AE over L multiplied by U3 is equal to the F. Now we know that U1, U2 and U3 are all equal, and we can substitute that in. We'll leave it in terms of U2. And finally we're going to get that F equals, substituting with U1, U3, we get that F equals 0 times U2. Now, it doesn't matter what value U2 is when you multiply by 0, it means that F must be equal to 0. And that can't be right because we've decided what F is, what the external force is, and unless it's 0, this system of equations doesn't work. Now, putting our engineer heads on for a second, we know looking at this system, but we cannot get static equilibrium, so you wouldn't get a meaningful solution from trying to solve this system. If you apply a force with no reaction force, then what you're going to do from Newton's laws is you're going to have a system that just moves. And picture doesn't want to scroll that well, but yeah, you apply force F, it's just going to want to move constant. Okay, so that doesn't make sense. When you use MATLAB or you try to use your graphics calculator, you're going to get some weird kind of error. I'm not sure what you get from your graphics calculator, but if you use MATLAB, what it's going to do is tell you that your matrix is singular to working precision. Okay, but in engineering terms, that means you have a system that's unsolvable.